All good. Okay, we can start the live stream. I think it can be live for some. Oh, it started. Yeah, that was okay. Okay, it's already streaming. That's good. So many messages. Yeah. All good. Okay. We still have 3 minutes, so let's go to prefetch. Well, yeah, if we can finish branch prediction, we'll prefetch. You can prefetch the branch predictions also. There's spots here too. Okay, cool. Okay. Okay, let's get started. So today we're going to continue branch prediction that Rahul started last time. Remember, you covered out of order execution and branch prediction, and we were kind of in the middle of branch prediction. I'll pick up on that, and hopefully we'll get to prefetching. I should say that these are two really fundamental topics in microprocessor design. If you don't get these right, then your processor would be, in my opinion, kind of useless. Because it won't be high performance unless you're not doing pipelining, of course, which makes your processor kind of useless to begin with. Useless in general cases, right? If you want to do general purpose computing. But in many cases today, you need performance. You cannot really cope up with the data. So you do need these techniques. And these techniques have been very fundamental. There's a lot of potential for growth in both, but more so in the prefetching part. Branch prediction is a bit much harder to develop these days. So that requires a lot more creativity and innovation, in my opinion. But that's true for prefetching as well. Okay, so you've seen some of these slides. I'm going to go through some slides relatively quickly just to fetch stuff in your caches, let's say. We're going to talk about, well, we have talked about compile time and runtime branch prediction. And we said that runtime is good because it gets rid of some of the issues that you have with compile time, which enables you to really predict branches based on behavior of the program, of the input data set dynamically, right? But this is more complex, clearly. And then we started developing predictors. One was 2-bit counter-based predictor, building on last time predictor. Essentially, one idea, the easiest idea you can come up with perhaps is if you want to predict a branch, you look at what happened to the branch last time, right? Which direction did it go? And we're talking about direction prediction in this case. And last time predictor was what we developed. But unfortunately, last time predictor is very quick to change its mind. So we added, as opposed to keeping only 1 bit in terms of what happened last time, you keep 2 bits. Like this is a 2-bit counter-based predictor that keeps track of what happened in the last n times, right? And then you can actually extend this by keeping more bits, etc. But this was one of the 2-bit counter predictors that we have discussed, right? So yeah, multiple states. So if you have actually 2 opposing outcomes, then you change your mind. You're predicting the branch taken, and if you see it not taken twice in a row, then you start predicting it not taken, and vice versa. Okay, so hopefully these are easy, clear. And then we went into more advanced concepts. This was kind of the state of the art until 1990s, the previous one, if I can get back to it. 2-bit counter per branch was the state of the art. You would store these in the branch target buffer, which you have seen also last time. And then people said, okay, this is not good enough. So we need to actually develop better predictors. And one was people realized 2 things. One is actually this paper in particular was the first one to realize 2 things. One is a branch's outcome can be correlated with other branches' outcomes that you've seen in the past. So it can correlate globally across different branches. And you have seen this predictor. Today, we're going to talk about local branch correlation, and then we're going to go off to other topics on branch prediction. But let me remind you of this global branch correlation. Essentially, there's good reasons why these branch predictors work. They're not magic in general, although later it starts becoming like magic because you really need to get to predictions. So there's correlation across different branches. So if the first branch is taken over here, then the second is not taken, then the second should not be taken also, right? So you can see clear correlations that we have studied last time. And this is one of the fun programs, actually, that was very, very difficult to predict using 2-bit counters. And with a global branch predictor, it became very easy to predict. So this is the equation to truth table workload and spec workloads in 1992. It was a very difficult benchmark for many processors until Pentium Pro implemented the global branch predictor with 4 bits of history. And then this benchmark was kind of useless. So you can see that benchmarks actually become easy targets if you actually have an improvement in architecture, and the benchmark becomes not interesting once you improved the system, right? Okay, so that's the story of equation to truth table, which is one of the Boolean workloads in spec 92. It's gone now. It doesn't exist. So how do you capture global branch correlation? The idea is to associate branch outcomes with global taken, not taken history of all branches. And you make a prediction based on the outcome of the branch the last time the same global branch history was encountered. So you keep track of the global branch history using a global history register. Each bit over there tells you which direction the last n branches went, okay? And then you use that to index into a table that recorded the outcome that was seen for that Gshare value in the recent past, hoping that that corresponds to your branch, right? And that's called the pattern history table. This is the same table of 2-bit counters. We used to index it using program counter. Now we index it using the global history register. Make sense? Okay. Okay. Yeah. The reason it has 2 levels of history is there's 1 level of history encoded in the global history register, and there's a 2nd level of history encoded into the 2-bit counters, which tell you what happened when you saw that global history last time, right? Okay, so this is what the predictor looks like, and I already said everything over here. This is the global history register, and this is the pattern history table. You index it. Potentially, you could use hashing, tagging, as we will see later on. But in this case, if you have n bits over here, you can have 2 to the n entries over here, right? Okay, this you have seen. Now we're going to get to the new items. So this was our, just to clarify everything, this was our one-level branch predictor, right? We used a program counter to index into this pattern history table that uses 2-bit counters for each program counter, or for a set of program counters, because you may use hashing to get there clearly, because you're not going to have a 2, if your program counter is 64 bits, you're not going to have a 2 to the 64 entry table of 2-bit counters. So use hashing normally. This is not shown over here. But this is essentially per branch, one level of history. This is our 2-level global history branch predictor. You use the program counter to get the target, but you don't use the program counter to get the direction. You use the global branch history to index into the direction predictor, 2-bit counters. So that's the idea. Now, something is missing over here. You're not using any program counter information, branch information, to index into the direction predictor, right? And people quickly figured out that doing that is a good idea also in this beautiful technical report by Scott McFarlane, who actually went on designed a lot of Intel branch predictors afterwards. Basically, the idea is to add more context information to the global branch predictor to take into account which branch is being predicted. So if you go over here, indexing the direction predictor using global branch history doesn't give you that context information. So this person wanted to add the context information. And how do you add that? Basically, you take the global history register and hash it or XOR it with the branch PC. It's very, as simple as this. And this actually immediately provides an improvement in accuracy for multiple reasons. First of all, now you have more context information. You don't just rely on the branch history register, which is the global history register. You also take into account branch address. So more information gives you better prediction accuracy. But there's also another benefit that you get over here, which is better utilization of the 2-bit counter array. So if you actually just use the global history register, as we did over here, you don't utilize as much. If you actually add more information, you have better randomization, let's say, over here. So you improve information as well as utilization. Now, the downside, of course, is this increased access latency. That's an XOR. It is on the critical path, potentially, right? Because you need to determine the next fetch address while you're fetching the current instruction. Make sense? OK, so that was new, Gshare. This is called Gshare, and this is a nice technical report that I would recommend people to read. OK, that's what Gshare looks like, basically. With some hashing, you hash global branch history and program counter and predict the direction. OK, now the question is, can we do better? We're going to talk about another type of predictability. So this was global correlation across different branches. But there's also local correlation for the same branch. For a given program counter, for a given branch, its outcome can be correlated with past outcomes that you've seen for that branch. Right? Makes sense. Clearly, there's something that is already exploited for this, right? 2-bit counters kind of exploit that. But they don't look at longer histories. So we're going to try to encode longer histories. And this is a nice excerpt from McFarlane's paper. Essentially, if you look at this loop, this loop test branch that's done at the end of the body executes a pattern that looks like this, 1, 1, 1, 0, which is taken, 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 not taken, right? Clearly, it's the loop iterates 4 times, right? So you can actually predict exactly what the direction of this branch would be as long as you know where you are in this pattern, right? If it's 1, 1, 1, 0, the next one will be taken because you're going to enter the loop. If it's 0, 1, 1, 1, the next one will be 0 because you're going to exit the loop, right? And that's the idea, basically. OK, this is kind of an unrolled version of that 1, 1, 1, 0. To predict a loop branch perfectly, we want to identify the last iteration of the loop. This is just one example, right? There could be other examples that you can come up with for local branch prediction, but loops are an easy example. By having a separate pattern history table entry for each local history, we can distinguish different iterations of a loop. And this nicely works for short loops, of course, right? If your history is, let's say, 4 and you iterate 4 times maximum, you can capture this. If your history is 16 and you iterate 16 times maximum, you can capture this. If your history is 256, now you need 2 to the 256 entries over here, or you need to be a little bit more clever. So this doesn't scale very well. That's why people have developed loop predictors, as we will briefly see. Make sense? So how do you capture this? Essentially, we're going to use the same idea. Have a per branch history register. As opposed to having a global history register that keeps track of the last n branches, we're going to have a per branch history register that keeps track of the last n times what happened to this branch. Right? I already said this, I think. You associate the predicted outcome of branch with taken, not taken history of the same branch. and make a prediction based on the outcome of the branch the last time the same local branch history was encountered. This is called the local history or local branch predictor. Again, this uses two levels of history. One is the per branch history register that I'm going to show you soon. And then there's a 2-bit counter history at that history register value. Okay, you could say that 2-bit counter history is kind of redundant, but it still gives you hysteresis in cases where you don't have these nice loops, clean loops, right? Okay, so the first level, as opposed to having a single global history register, we have a set of local history registers, ideally per branch, but that's not easy to do, of course. So we're going to have a local history register per set of branches indexed by some program counter. Think about that. Okay, n bits each. You select the history register based on the program counter of the branch. That gives you the local history for that branch. And the second level is the table of saturating counters for each history entry over here, the direction the branch took the last time the same history was seen. Make sense? With hysteresis, of course. Okay, those are 2-bit counters. I mean, they could be 3-bit counters. As you will see, there will be 3-bit counters for some alpha processor. It depends on how you your programs, etc. Okay, so this is what it looks like now. This is what the local history predictor looks like. You take the program counter, you index into this table of history registers per branch, and based on some bits in the program counter, you select the history register. That's the first level of history. Using that, you index into the 2-bit counters, direction predictor. Now that gives you the highest bit over here, gives you the taken, not taken prediction. Makes sense, right? Okay, that's the local. Now we're taking into account 2 levels of local history. So that's which directions earlier instance of this branch went. Okay, so that completes global and local prediction. And you can actually generalize this. This is actually the next version of this paper in ISCA 1992. I still reference this because this is the earliest paper. Generalized it. It basically says you can have a branch history register that could be global, or it could be per set of branches, or it could be per branch. And you can have a pattern history table that could be global or per set of branches or per branch. Right? All of these can be per branch as well. And there are different variations of it. And the pattern history counters, the 2-bit counters over here, can be determined by the compiler, or you update them dynamically. That's what adaptive or static means. Adaptive means you update them dynamically. But you could imagine a case where the compiler determines them, right? It's a tough job for the compiler, but you could imagine it. So that's why they don't use the S portion over here. Though GAG, for example, has a single global history register with a single global pattern history table. And these are all adaptive. And this is the most frugal global history predictor that you can get. And this is what's implemented in Pentium Pro. And that's what made partially Pentium Pro successful. Pentium Pro was the real first processor that implemented both out-of-order execution and aggressive branch prediction at the same time. It was the first commercially successful out-of-order processor that made Intel rich, let's say. Intel's having problems right now for different reasons, but Pentium Pro was a good architecture. Okay, so on the other extreme, you can have a branch history table per branch, right? Every single history register belongs to a separate branch over here. Clearly not realizable in reasonable hardware. And then basically you have this also per branch. So that's also clearly not realizable, right? This is the most expensive form, which this is not realizable. So usually what you have is some combination in between. It's usually actually SAS, which is not shown here. You have a per branch history table for a set of branches, and you have a global pattern history table per set of branches. In fact, Pentium Pro was actually per set of branches, I should say. To be really exact, it was GAS. It was not GAG. Make sense? Okay. Anyway, you can read more about this, but this is a nice taxonomy. Now you can actually beautifully evaluate all different types of predictors. You have a simulation cluster, and you have your workloads, and you can figure out the branch prediction accuracy for all types of predictors. Okay, and this is a retrospective or that paper. It won the Micro Test of Time Award. It's essentially implemented in all processors today. I'd recommend reading that. That's the entire retrospective in 2 pages. Okay, the question is always, of course, can we do better? Any questions, by the way? Okay, everything is perfectly clear. You're implementing this sort of this thing anyway, hopefully in your labs. More interesting things, of course, today. Okay, can we do better? And people have figured out that they can do better. I'm going to give you several ideas over here. One is basically there's no good algorithm for every single branch. Essentially, predictability of branches varies across branches. Some branches are more predictable using local history, for example, loop branches. Some branches are more predictable using global history. For example, branches that are dependent on prior branches that are executed, like we have seen earlier. For others, the simple 2-bit counter is enough. Yet for others, a single bit is enough, right? In some cases, actually, you don't even need branch prediction almost, as Rahul described, right? You can do program analysis and say, oh, this branch is testing for an error or a null pointer. And if that branch is, I'm guessing that that branch is never going to be taken unless the program is wrong. And if the program is wrong, I have other things to care about than getting that branch correctly predicted, right? So if you can classify your branches nicely, you can design different predictors to cater for different branches. So basically, there's heterogeneity in predictability behavior of branches, and there's no one-size-fits-all branch prediction algorithm for all branches. And the idea is, whenever you see no one-size-fits-all and heterogeneity, you can think about a heterogeneous design, right? So you can exploit heterogeneity in branch predictability by designing hybrid branch predictors, which are essentially all predictors today. And this is what was also proposed in McFarlane's paper. In addition to proposing the Gshare predictor, he also said, okay, we need to design hybrid branch predictors for the reasons that I discussed in the previous slide. And the idea is to use more than one type of predictor to select and select the best prediction. For example, you can have a hybrid of 2-bit counters and global predictor. You can have a hybrid of global and local. You can have a hybrid of multiple of these, etc. Clearly, this makes things more complex. That's one of the disadvantages. But this gives you better accuracy because of the reason that I just discussed. Different predictors are better for different branches. But there's also another benefit, which we kind of glossed over in the design of prior long history predictors, right? If you have 2 levels of history, it takes longer to train that predictor. Imagine a predictor with 16 bits of history, a global history register. In order to train that, you need to see the different outcomes over time, right? And imagine now per branch local histories. That actually takes longer time to train. So there's a warm-up time to actually train the predictors such that you are operating at the steady state. And if your predictor is not ready yet, you can actually use the faster warm-up predictor. A faster warm-up predictor can be backward taken, forward not taken, right? We have seen that also in last lecture. It could be some other hint, something simple, basically. Clear disadvantages: complexity, more hardware and complexity, even longer access latency. And you need also a selection mechanism. The question is, how do you design that selection mechanism? Which predictor to use is determined by a meta predictor or a selector. I'm going to give you some examples, and you're going to implement this predictor, actually. This is what's implemented in Alpha 21264. All of these hybrid branch predictors are actually implemented in all modern high-performance processors. But the Alpha 21264 was a beautiful out-of-order execution engine. And Alpha actually put a lot of information about it at the time. So they actually explained how this works. In this processor, minimum branch penalty was 7 cycles, but typically they saw in workloads 11 plus cycles. And this was one of the fastest processors of its time, actually, in terms of frequency also. Okay, they did some target prediction. And this was what the predictor looked like. And you can see that it's a global history predictor over here. Very similar to what we have seen, 12 bits of history. And then you have a local history predictor, a local history table and local 2-bit counters, pattern history table over here. So this used 10 bits of history over here, and then 3 bits of counters, not 2-bit counters, but 3-bit counters. Why? Because they decided that that worked better for their workloads, right? And then you need to do a choice prediction over here. And they basically use the global history. They basically kept track of which predictor was doing more accurate predictions based on the last time you encountered that global history. Again, that's their choice. You could come up with better mechanisms, potentially, right? Make sense? This is also a beautiful paper. If you have time, I'd recommend reading these papers. It's a very fundamental paper that talks about a lot of issues in high-performance out-of-order processor design. And we're talking about 1999. Today, we're in 2025, right? And people are designing processors of 2028. So a lot has been optimized, but this is a good baseline to think about. Okay. Let me talk about biased branches, because this is one way of also making the predictor less, let's say, do less work. So basically, people have found out that many branches are biased in one direction. For example, 99% taken. If you're doing a loop, for example, in many iterations, that's taken most of the time, right? And these branches actually pollute the branch prediction structures, meaning make the prediction of other branches difficult, but because they cause interference in branch prediction tables and history registers. So the solution to this is detect these biased branches with some quick detection mechanism and filter them out. And predict them with a simpler predictor. It could be a last time predictor, it could be a static predictor, it could be something that you design. Make sense? So how can you detect them? You can actually think about detecting them at compile time or runtime. Having a simple detector is not that difficult. Okay, this is proposed in this nice paper, Micro 1994. Again, we're talking about early times. If you're interested, you can read that. And people employ these mechanisms so that the hardware, you don't want to waste your hardware for things that are easy, right? That's the idea over here. You want to focus your hardware for things that are difficult. We're going to see that idea more and more soon. Okay, so basically, are we done with branch prediction? So a lot of people said, oh, these hybrid branch predictors, we're done with branch prediction. Because they work reasonably well, maybe 90 to 97% prediction accuracy on average at the time on some workloads. I think the workloads today are much worse, frankly, some of the harder workloads. But even then, difficult workloads existed. For example, one difficult workload is a compiler, GCC. This takes a lot of different paths based on the input set. And the paper, I think this was McFarlane's paper, that showed that maximum instructions per cycle you could get with tournament prediction is 9, if you remove some of the other constraints in the machine. But maximum IPC with perfect prediction is 35. That's almost 4x, right? So this makes a good case for working on branch prediction. And I think Rahul made a good case earlier by showing you the, in terms of like, if you get to 80%, you're still wasting a lot of instructions in the machine, right? So there's an energy efficiency case to be made as well. Okay, so I'm going to talk about some other branch predictor types that are employed in existing processors again. So we talked about loops. I'll go through this relatively quickly, but you can detect loops. People figured out that you can actually, if the loop iteration count is predictable, you can predict that iteration count and filter those loop branches out. This works well for loops with especially small number of iterations where iteration count is predictable. And Intel Pentium M was one of the first processors that employed it. We're going to talk about Perceptron that essentially uses very simple machine learning technique. How many people know about perceptrons? No one. Okay, you're going to learn about, okay, one person knows. Don't be afraid. It's okay not to know. I guess it's not okay not to learn if you're interested to learn. Yeah. Okay. Basically, it learns the direction correlations between individual branches. Learns, I guess, for one form of learning by assigning weights to correlations using essentially perceptrons. We're going to talk about that. And then we're going to talk about using different history lengths, because people also figured out that there's no one single history length to predict every branch. Some branches are predictable with short histories. Some branches are not predictable with very, very long, very long histories. So you want actually heterogeneity in histories also. And this predictor actually adds heterogeneity. Okay, I will not talk about this, but essentially you can detect a loop by monitoring backward branches and seeing how many times that branch is taken and keeping track of essentially a limit that you learn or record the previous time a branch is executed and seeing whether you have reached that limit the next time you actually started taking that branch. Make sense? That's a loop detector. Your life may be easier if the compiler actually marked the loop branches right. Then and the compiler actually hinted that your loop branches may be even predictable, right? Some loop branches are not that predictable, of course. So this is employed. You can look at that. And this is a nice paper. This was during the time when people used to write more or less informative papers about their architectures. People are a lot more, let's say, protective these days of their architectures. Unfortunately, I think people, it would be much better if people shared their architectural designs. Okay, so this is kind of a little bit off topic. We're talking about direction prediction, but never forget the target prediction as well. There are indirect branches that exist in our systems, and these have different targets. You basically jump to a register, right? So people design predictors for that purpose as well. So some of the ideas that we've discussed can be applicable. Like based on the global history, you select the target from the BTB. But there are other ways of doing this, which are actually quite interesting, but we don't really have time to cover everything in this course. Otherwise, we may have several lectures on branch prediction. Okay, so this is Intel Pentium M, and according to them, this is the branch prediction logic. I would probably say that this is probably the fetch part of the logic without the iCache, but it's actually substantial, as you can see. Okay, let's talk about more advanced branch prediction. Feel free to ask questions, by the way. Okay, yes.
It's probably not a stupid question, but as you saw in the picture earlier, there's a lot of surface area taken up in this kind of prediction alone. Wouldn't it also be probably less efficient with energy, but you just replace those with cores and then just force it away from a lot of the predictions now? And I don't know if that'd be more, probably less like the efficiency, but I'm assuming people have done that.
Yeah, I mean, people have certainly done that, right? That's an approach taken by other companies like Sun Niagara, which is kind of dead right now. So basically, the trade-off is, do you want higher performance in a single thread, which most of the world is still, unfortunately, or do you have many cores? Do you dedicate this area for many cores and hope that people will write parallel programs? Yeah.
The local, where is it stored? Is it in the memory?
No, these are dedicated hardware structures. So you have an SRAM array where you store the, yeah, exactly. So these are all dedicated hardware structures in the branch predictor. I mean, if your hardware structures are large, then you can think about potentially virtualizing the predictor and putting things into the L1 cache, etc. But complicates things a lot. Yeah, exactly. Yeah. Any other questions? Okay. Now let's talk about Perceptron, since many of you may not remember or may not know it. This is developed in 1950s. It's really the, I guess, smallest type of, I don't want to even call it a neural network. It's a one-layer neural network. Basically, it's a simplified model of a biological neuron, as people understood at the time. It's also a simple binary classifier. Basically, it maps an input vector x to a 1 or 0. So this input vector can be something, and you basically classify it to a 0 or 1. And you interpret this 0 or 1 in different ways, right? It could be, for example, an input vector of words, and you run it through some weights. And after the multiplication, you get a 0. Am I seeing German or am I not seeing German, right? This is what kind of classifiers do neural network, but this is one of the simplest form of things. But let me make it more clear, and let me put it in the context of branch prediction. So input is some vector x, essentially a bit vector. Perceptron learns the linear function, assuming one exists, of how each element of the vector affects the output, stored in an internal weight vector. So we have a weight vector also that it's going to learn. Now this is kind of looking like branch prediction now. Input vector can be the global history register, and output can be whether should I predict this 0 or 1, taken or not taken. And the weights essentially map to how each bit in the global history register affects the output, right? So you learn the correlations between that bit and the branch you're predicting. That's the output. That's how you calculate the output. You basically multiply the weight vector, internal weight vector that you learn, with the input vector x. And then there's a bias also, but you could remove the bias. We're going to talk about that briefly. And if it's greater than 0, you predict the branch. Okay, in the branch prediction context, vector is branch history register bits. Output is prediction for the current branch. Makes sense? So this is the paper that proposed this in HPCA 2001. It also won the Test of Time Award in HPCA. It's used in many processors today, maybe not all, but many. Essentially, the idea is to use a perceptron to learn the correlations between branch history register bits and the branch outcome. And a perceptron learns a target Boolean function of n inputs. So let's take a look at this. This is, oh, it's animating something. So these are the inputs, x's, and this is the bias bit. And these are the weights over here. Each branch is associated with a perceptron. A perceptron contains a set of weights, which are shown kind of like this here. Each weight corresponds to a bit in the GHR, global history register. It represents how much that bit is correlated with the direction of the branch. So if that bit is correlated positively, meaning if that bit is 0, then you will likely take the branch, for example. You store a large positive weight associated with that bit. You learn this, of course. You train this. There's some training algorithm that I'm not going to go into, but you can read the paper. And negative correlation means you have a large negative weight. So you express the GHR, global history register, as 1 taken and -1 not taken. And you take a dot product of the global history register and the weights. And if output is greater than 0, you can predict it taken. Makes sense, right? Assuming you've done the training accurately, correspondingly. I will not go through this, but this is the prediction function. There's a bias weight independent of the history over here. This encodes the bias of the branch. And there is dot product function of the GHR and perceptron weights. And you can see that based on the branch address, you get a table of perceptrons, which are the weights. You select the perceptron and you multiply it with the history register, and then you get the predicted branch outcome. And then there's a training function. These could be different types of training functions, but you can read the paper for more detail. Okay. Hopefully this makes sense at some level, right? You could train a convolutional neural network also, except it's much more expensive to train that thing. Even this is expensive, right? We were talking about, we start talking about multiplications right now, right? We're doing multiplication to predict the branch. And you were saying this is a lot of area. Well, there's more area coming, basically. And how do you optimize these multiplications, etc.? Right? People implement this. This exists. Okay. So advantages. Clearly, there's a more sophisticated learning mechanism. You get better accuracy. And this is real. When I was doing my PhD, I implemented the Perceptron because I needed better branch prediction accuracy, as we will see later on. And I immediately got a 20% improvement in terms of branch misprediction rate. Yes?
So when we talk about a perceptron branch predictor, is this predictor actually trained like on the fly while the
yes.
system is warming up?
Yes, absolutely. Yeah. Yes, it's all online. There's also there's all hardware for that.
So this is not for like the entire program then, or like?
No, for each branch. Basically, for each branch, you have a perceptron. So if you look at this table over here, well, each set of branches, right? You have a hash function that takes the branch address, and there's a perceptron associated with that. Right? Okay. It can get better over time if there's this sort of correlation. Okay. It enables long branch history length, actually. This is better accuracy in a different way because your Gshare can be very wide right now. And assuming you can tolerate some sort of aliasing in this table, interface in this table, you don't need a huge, let's say, 2-bit counter. So now we don't have 2-bit counters, as you can see, right? That's gone. It's a different way of thinking about the problem, which is what we should be doing, I think, going forward in the future. Okay, there are disadvantages, of course. Clearly, there's complexity. There's an adder tree to compute the perceptron output, meaning a multiplier. People try to simplify it. There's a lot of work that tries to simplify it, but it's still not simple, right? There's latency also, right? How do you get the latency? Because it takes time to actually do this computation, right? There's another disadvantage that later works actually try to fix. Perceptron can only learn linearly separable functions because of the way it gets trained. It cannot learn XOR type of correlation, for example, between 2 history bits and branch outcomes. So it cannot learn everything nicely, let's say, even if there's this type of predictability. Okay, but this is a successful example of machine learning in processor design. Maybe the only real successful example today. Only is maybe too strong. For example, Samsung. This is an interesting paper because this is a product from Samsung. None of the authors are from Samsung because they disbanded their architecture team, which was not very forward-looking for them, in my opinion. But they actually tried a lot of interesting things in this Samsung architecture, including a perceptron predictor. And another thing is actually one of the ideas that we had written in ISCA 2007 that was called virtual program counter prediction, a way of doing indirect branch prediction by using the conditional branch predictor and not adding additional hardware, at least large amounts of hardware. So there are a lot of innovative ideas, in my opinion, in this paper, including Perceptron. Later, AMD also, well, maybe not later, but around the same time, developed its own Perceptron predictor. So you can see that there's a hashed Perceptron predictor, which you're going to implement in your lab. There's also Tage, which we're going to discuss soon. So they actually had 2 levels of prediction over here. So you can see that the prediction logic is getting complex because these processors need better prediction accuracy for reasons we've discussed in the previous lecture. And you can also see that BTBs are also getting larger branch target buffers, right? There are multiple levels of BTBs to predict branches. So what does it mean to have multiple levels of prediction? Essentially, if you actually you have one level of prediction to quickly predict whether the branch will be taken or not taken, and you start the other prediction that takes longer. And if the other prediction is more accurate, you basically flush the pipeline earlier based on the better prediction, right? The branch is still not resolved yet. And then you may actually resolve the branch, and then you figure out that you flushed the pipeline wrongly or correctly. Yes.
And how do you determine what's more accurate?
Well, again, you can keep counters. Yeah, very similar to what we have done with the hybrid branch predictor, right? Earlier. You can keep counters as to which one's doing better, which predictor is doing better, for example. Okay, so this is, I'm not going to go through this, but this is from some, it essentially shows that there is a table of perceptrons in Zen 2. And I kind of like what they've shown over here, even though they may not be perfectly correct. I think there should be a plus over here as opposed to multiplication. Okay. Okay, so the lab one is nice because you will get to actually progressively improve branch prediction accuracy and maybe come up with your own ideas. We already start with a 2-level global history predictor. And then you implement a 2-level local history. And then you implement a tournament predictor similar to alpha 21 to 64. And then you implement a simplified perceptron predictor and hopefully observe accuracy improvements, right? And then you can actually exercise your creativity and come up with better predictors. I think Sage already exists, but I'm going to talk about that. Okay. Okay, let me talk about another idea that has been quite successful. And the idea I've already given you, basically, using multiple history lengths. Essentially, people have observed that different branches require different history lengths for better prediction accuracy. And the reason for this is actually based on the program, because some branches correlate with branches that are very close to them in the program. Some branches correlate with branches that are much farther away. Imagine that you're testing a condition here in the program, and there's a huge loop with lots of branches, and that condition was somehow set before that loop, right? Maybe you executed thousands of branches until you get to the branch that tests that condition, right? For some reason, it could happen. So the idea over here is to have multiple pattern history tables indexed with global history registers with different history lengths, intelligently allocate pattern history tables to different branches. So it kind of looks like this. So you can see that this is a PC-based predictor, 2-bit counters potentially. It doesn't have any history. You can see that there is one level of history over here, short history, and then longer history, and then longer history, and then longer history. And these folks showed that with geometric history lengths, geometric series of history lengths, you can actually get a nice predictor because you can cover a large set of history lengths. And they actually add tags over here. You can see that basically. So you hash the PC with history over here, and then you tag it. So what happens is, how do you decide which one to use? You use the, well, there are many heuristics over here, but based on the confidence, you can have confidence bits that we will talk about later. But you could also use the history length that matches your tag, for example, right? The longest history length that matches your tag. So clearly, this complicates the prediction right now. But it turns out this gives you a better prediction accuracy. And this was developed by André Seznek and Pierre Michaud. And these guys are actually kind of magicians, in my opinion, of branch prediction. André designed a lot of branch predictors of very different processors. But this is an example, right? You use this history length for a branch like this. You use this history length for a branch like this. You use this history length for another branch that may be more difficult to predict. Again, this is not the best picture, but that's the idea. So the advantage is you choose the best history length to predict each branch, hopefully best. This depends on how you train this thing, how you actually decide what to use. Hopefully you get better accuracy. And again, this is real. You get better accuracy in real systems. It enables long branch history lengths, and it gets you better accuracy. So Perceptron enables long history lengths by having large weight vectors, right? Here you enable long history lengths by having tags, for example, right? Meaning you can have a 1024 history length over here, but you don't need to design a 2 to the 1 to the 1024 entry 2-bit counter, right? You have a small table, and hopefully you only allocate things over here when you don't have a good prediction over here, 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 here. Make sense? Clearly, you need to take that into account. Yeah, exactly. Hopefully, this is kind of a last resort. But if you have a good classification, hopefully you bin the different branches to the right history length over time as you train things. Okay. Yeah. Okay. So there are two advantages, basically. You take advantage of different histories. You also enable long branch history lengths because of the design of the predictor. Of course, it comes with disadvantages, more hardware complexity, right? You could argue which one's more complex, Perceptron or this. I think Perceptron is a little bit more complex because of the multiplication. This is, in my opinion, this is easier to implement. As a result, it's implemented in essentially all processors today. I cannot say that for Perceptron exactly, even though it has been very impactful. It still has these operations that are not, let's say, that we want to avoid in general. Right? Okay. So the question, of course, the disadvantage is that large design space is large. You need to choose good hash functions and table sizes to maximize accuracy and minimize latency. And again, this is another successful recent idea. So as I said, AMD Zen 2, starting with Zen 2, they implement Tage as well, in addition to Perceptron. And they use Tage as an L2 predictor. I don't know if they still do, L2 meaning level 2. So if the Perceptron is deemed to be not so accurate for a branch, they correct it using Tage. Okay, this is again from that picture. I think they got this one right. Okay, so why do we do this? Actually, people have analyzed. This is a beautiful paper that looks at predictability of global branch. So clearly, it takes a global predictor. Right? You could implement a local predictor next to it, but I will not talk about that. As we will see, we'll talk about the loop predictor soon. But there's this paper that looked at a lot of programs at the time, and it's tried to figure out which branches really matter. So you may have a 1024-bit history going back 1024 branches. For some branches, you need to go 1024. For some branches, the just previously executed branch is the one that really determines your direction, or that really correlates most with your direction. The problem is you don't know which one's which, right, beforehand. That's why you need to have different types of histories. And for different branches, you have different distances between correlating branches. So if you're interested, you can read this paper. It's a beautiful paper. Okay. Question is, can we do better? All the time, right? Okay. Basically, this is the state of the art in branch prediction. I'll give you two ideas. This is from Andres Sesnek again in Championship Branch Prediction 2014, which you could participate in after you take this class. We're very close to state of the art at this point. You just need to optimize things better. But basically, this what this does is it's an interesting predictor. It starts with a main Tage predictor using global histories. It gives you a prediction and some confidence levels, which we will talk about, how confident you are in the prediction, basically. And then it has a statistical correction mechanism that takes into account a lot of things, global, local, and what he calls skeleton histories. You can read about that in the paper. And then there's a loop predictor. Basically, it corrects the prediction over here using some more information. And then it decides whether it's a loop branch or not. And then it decides the prediction. So you can see that this is a hybrid predictor. It's a little bit different from what we've seen in Alpha 21-64, but the hybrid idea still exists over here. And then there's some correction idea. Okay, and this is all open source. You can actually, it's actually implemented in the lab 1. So you can actually use this. If you submit this, you'll get 0 credit for the last portion because it already exists. But you could potentially improve it. Okay. So people have actually started experimenting with more things. So after this, there's been a lull in branch prediction, in my opinion. There's works, but nothing that actually had the impact that Perceptron and Tage had. More recently, people have started developing ideas. This is not implemented yet because it's a bit complex. I'll just give you the basic idea as opposed to going into details, because the details, devil's in the details, actually. And there are a lot of devils in these details, in my opinion. But basically, it's good to experiment. So these folks said that you could train, essentially the problem is, if you have a large, noisy global history, identifying the correlation between a branch's outcome and what it correlates with is hard. So, but we can potentially identify these correlations with things that we know identify correlations nicely today, right? Convolutional neural networks. Right? You use global history to expose those hidden correlations, but only for hard to predict branches. Don't do it for all branches. If the branch is not easy to predict, use a convolutional neural network for it. So this is trained offline. So you actually set the weights offline because online training is very expensive. And you hopefully, assuming you set the weights nicely, you get better prediction accuracy. That's what this paper shows. And they use Tage SCL for all other branches, which is this. Yes?
So, but the CNN usually takes quite a couple cycles to just shoot the prediction.
Evaluate, right? Yes.
So how do you manage to do that in one cycle?
Yeah. Well, you don't necessarily do it in one cycle. You need to do a lot of pipelining, look ahead predictions. So there are a lot of works that try to, that's actually true, not just for CNNs, by the way. All of the predictors like Perceptron, Tage, these are actually long, complicated prediction mechanisms. You need to do a lot of stuff, a lot of tricks to get the prediction before you really need it. So you can apply some of the tricks, but CNN makes it much worse, of course, right? So there's something called multiple block ahead prediction, for example. You try to predict branches ahead, much longer ahead, so that you overcome that latency. That's a very good question, though. I mean, people actually deal with these things. Designing this predictor, any of these predictors is not easy. Convolutional neural networks makes it much worse. Yes? They have their own units. These are all customized hardware for branch prediction. Yes. Okay. Let me, yeah. But this is fun. I mean, people actually, this is one of the funnest part of the processor design, maybe except for prefetching. I'm biased. Okay, let me finish these slides because we're almost at the end. I will cover a very easy concept comparatively. The idea is branch confidence estimation. So we've been talking about hard to predict branches, hard to predict branches. One way of estimating this is using confidence. This is actually an idea that was developed in the 1990s also. And the idea is to estimate if the prediction is likely to be correct, how confident the predictor is in the prediction. Why? Because this could be very useful in deciding how to speculate, what predictor to use, whether you want to keep fetching on this path, whether you want to switch to some other way of handling the branch, like some eager execution or predicate execution, many other things basically. So this is one example estimator, but people have used more recently Perceptron-based estimators also. So there are many different types of confidence estimator. So very similar to what we have seen, branch address, global branch history register. You keep a record of correct and incorrect outcomes for the past n instances, and based on the correct and incorrect patterns, guess if the current prediction will likely be correct or incorrect. There are better ways of doing it today, which I will not go into. So one thing that you could do clearly is selecting which predictor to use, right? But another thing that you could do is what's called pipeline gating, which is a nice idea. It's harder to implement today compared to 1990s because today processors are not that simple, let's say. And the idea over here is you keep track of how many branches that you fetched into the machine that are low confidence. And if it's greater than some threshold, you stop fetching so that you don't waste execution. You could switch to another thread also. You could do something else, etc. Make sense? Okay, so this is my last slide. So if you're excited about this and if you enjoy the lab, you're actually going to be using the infrastructure that this championship branch prediction develops. You can actually compete among yourselves, but you can also compete globally by submitting to this championship branch prediction. The deadline is May 2nd. The goal of this championship branch prediction, this is, I think, the 6th edition, right? Last edition was, I don't know how many years ago, maybe 5, 6, 10? 16, okay, 10, almost 10 years ago. So I didn't guess completely wrong. So this is to actually develop ideas in this domain and encourage new ideas so that we can make more progress. So if you're interested, feel free to talk to us. We may encourage some of you if you actually develop a predictor, for example, in your lab. So we're not done yet, but the bar is pretty high. Okay, but we're done with the first part of the lecture. Now let's be back when the bell rings, and then we can continue with prefetching.
I think it only seems like I don't trust this hard Prefetching all that much, to be honest. But I've seen that it happens for most of the workloads that go above 50 million instructions. Yeah, like this one here has gone through 68 million instructions instead of yes. However, I found out if I were to set this to like 500,000, so let's not try my laptop, and run it. Yeah. Just well, when I did it in the morning, I was quite worried about it actually. But yeah, it's M2 Pro, but it goes up to like 50 watts power draw and heats up to 100 degrees almost. Why transfer is my specific? Oh, there it is.
we just go to that specific trace and say just run that.
That's the trace that was going for
This one.
So let's do this instead. Oh wait, I have to do a single trace run in that case.
Just dot slash C.
Yeah. Slash, let's do
dot slash CVP.
Oh, that's not sorry. Oh no, I get it. 50 million and then
Let's keep it small.
I mean, if I 50 million, it goes through in like a minute. Okay.
And then let's say minus H.
And then the trace directory is inside CDP, six traces. Then we need there we go. That definitely, yeah, that definitely finished with
Okay, so it's finishing with 43K. It's 43K is decent, and it's not going to run exactly 50 million, but some. No. So I said 500K, so it's coming around 538K, right? So it's fine.
I think we should increase the heartbeat now, because I think the print statements of the heartbeats are actually more detrimental to the update.
This is 5 million.
Yeah, it's 5 million. So we're halfway through now.
Okay.
Is it 100,000?
Yeah, it's 100,000. So now we're almost done.
It's coming up, right?
Yeah.
5 million, it's coming around. So it's not 5 million, it's 4.6. Yeah, I mean 438K, but when you give it. Yeah, so if I said 500K, now we give it 50 million.
I think now that we're at 500 million.
Yeah. 1, 2, 3, 4, 5, 6. Yeah.
Okay. 50 million. That will probably take a couple minutes now. How bad it goes for my CPU here tomorrow. What? No idea. Yeah.
And an edit simulator, so it's going to.
Yeah. Yeah,
So you have it in your power.
I have it on my power bank, yeah. Yeah. The only thing I'm really worried about is usually like the max core temperature. Because this one spiked to 100 degrees. Last time when I did it. Yeah, right. I think it only spiked because I was multi-core. It was multi-coring everything at the same time.
Yeah. So if you're running all of them all the time, then that's really too much. So just try out with more simple ones. So this is yeah. So this is 1 million.
My power bank went on battery, so I'm frozen. Like this power draw is probably frozen. But yeah.
Okay. But I think it's going to finish in 5 minutes.
Yeah, it should.
So can I just make sure? So all the ones that we are seeing, it's finishing with a 70 million, even though you are supplying 50 million.
Yeah.
If it is finishing earlier, it's mostly because the trace itself is doesn't have those restrictions. So that's fine. If it is going much later, like not you provided 50 million, but it's going beyond, let's say, I mean 5 million is fine, but beyond that, it's probably something problem.
Yeah.
So
I have the suspicion that this because like this was edited by me, of course, that it maybe actually disregards this part here.
Yeah, probably we need to change the script. So just write it to us. Probably we can auto.
Yeah.
So the script is.
I'm mostly like I would think because this was added. I think it was added either. Oh wait, maybe. Oh, maybe I actually did the miss. I actually maybe wrote 500 million. That could be a problem.
Yeah.
If actually
okay,
just
then,
came to my mind because
Then we got that point.
yeah, because we almost missed type here as well.
Yeah.
If you of
that might
course
be it.
write 500 million, we don't block it.
That's
That's probably what
maybe you can
happened,
just simply
yeah.
put it somewhere that it's 50 million and then just a hard
Yeah.
I think it is going to finish the company. So this is 2.
Yeah, it should.
He said 50 million.
Yes.
Oh, it's going to take halfway.
Yeah, we're halfway through.
So
So
no,
1.5 minutes, 2.5 minutes, and then we're through.
Are we halfway through?
and yeah, we're 2.5, right? 25 million.
Yeah.
Is this 20? Oh, yeah.
Yeah, it is.
Yeah.
And we were like at 130
Yeah, I'm
seconds.
reading
So.
less. I'm reading a 0 bits. Okay. I think it's going to be.
Yeah.
Did you see the email I sent you about the WhatsApp group?
You just said
No, I sent it last week. It's okay. Because we wanted to set a WhatsApp group for the class.
okay.
And we didn't know if everyone was at the lab last time.
I see. So
So I sent you a WhatsApp. Oh, I sent you an email for WhatsApp link. And I was hoping you could put it onto the Moodle thing.
okay, maybe I'll check that. Can you bump me up on that?
Yeah,
email?
sure. Yeah.
It's fine. What's the this one?
I think I sent it from my private email by accident, so I think it
No,
might be a bit
it's
on there.
what's the subject of the email? What's this?
Oh, this is the figure I created. I wanted to ask if this is like what you imagined.
Oh, this is the number of instructions that have been missing.
Yeah, no. So like basically, this is just like a heads up how many instructions were executed, and here is the MPTI.
Well, we're running Gshare, but if you want to first get a taste of what the state of the art is, we just simply run the playlist.
Oh no, this was requested for the task.
Yeah, I know. So I'm saying if you just want to see like what playlist it is, you would just simply pull down everything. Like everything.
Yeah.
This is probably going to. I mean, it's still not good that probably come around this 25-ish.
This I think it finished within like 20 minutes or 50 minutes.
Okay.
I sent you a hope that worked. It's called WhatsApp for Boca.
Wait, I can actually tell you how long it took. The CSV is quite extensive. So like you see here execution time. So I mean of course these were parallelized.
This is your Rockwood data. That's the point. Yeah, it's sent from my private email. I'm assuming it's the really big one.
27 seconds. Yeah, but like these of course is parallelized, so it might be like maybe all of this summed divided by 8 because I think I have later for each course. Oh no, this shoots up. If you use the script, it creates new threads. It bombs every single core you have into oblivion. Oh, by the way, the 443,805,000.
Yeah, that's fine.
Oh.
Plus minus.
Yeah, 43 million.
Yeah, plus minus finish.
Trace exit training class.
Say it again. Okay. All right. Sounds good. Okay.
And then you see if I execute this.
Is everything okay online? Yeah. How about now? Can you hear? Okay. Awesome. Is all good? Everything good? Yes. Okay. Okay. Let's get started then. Okay, now we're going to switch to prefetching. But I should say that branch predictor design, as you have been figuring out, is not easy. It's a very tight loop, especially at higher frequencies, lower clock cycle times. How do you get that next prediction in a single clock cycle is not easy, and it's difficult in general. sometimes you may get bubbles. So it's good to have a predictor that can make a quick decision, and then another level of predictor that can make a correction, and then maybe another level of predictor that can make another correction. So you normally have in existing processors multiple different places where you flush the pipeline based on a potentially incorrect prediction. Not just one place when the branch is resolved, but there are intermediate steps where intermediate, increasingly better branch predictors make a better prediction. Okay, now we're going to switch gears and talk about another fundamental problem, which is prefetching. But I will motivate it with other things. Okay. I kind of use memory latency problem over here, but you can ignore memory, ignore latency, and then it becomes a problem. And that's the problem we're going to focus on, the problem, which is the real problem that we have in our systems today. How do we get rid of this thing? Annotate. Okay, it got rid of itself. You can call it the latency problem, you can call it the memory problem, or you can call it the memory latency problem, or you can call it the problem. Pick your choice. So basically, memory latency lags behind. This is across, let's say, 18 years of DRAM improvements. Capacity has been improving, bandwidth has been somewhat improving, latency has not been improving. And these are real DRAM chips. I'm going to show you a better picture and refer you to a paper. And as a result, we are not able to feed data nicely, and we cannot tolerate those latencies easily. This is actually a study of 54 years of chips, DRAM chips. And I would recommend that paper if you're interested. This was done by Minesh Patel, who was my PhD student, who's a professor at Rutgers right now. But basically, you can see that capacity has improved pretty well over the course of 50 years. That's a 1,000,000x capacity improvement on a DRAM chip. People have tried hard. It's kind of slowing down a little bit, but still, people are pushing it. And this is what happened to latency. 8x latency improvement over the same course of 50 plus years. 1,000,000x plus versus 8x. And more recent years, last 20 years, you can see that this is almost constant. Some of them are going up. So latency has become much harder to improve, partially because it's fundamentally harder to improve. The technology is not necessarily on your side. And also because interconnects are not scaling as well as logic, let's say, or even the capacitors. And also, it's a design choice that people make because cost per bit is what drives the industry with a mindset. And latency is not the driver, let's say. Okay, this is the paper. If you're interested in all of that data and more, I'd recommend looking at that paper. Okay, memory latency is clearly critical for performance. We're going to later see lectures on processing in memory, etc. We're not going to do that now, but it becomes a performance bottleneck. And there are papers that are showing that this becomes worse with some new DRAM types because some of the new DRAM types actually increase latency so that you can get better bandwidth. Okay, again, you can look at some of the papers. Okay, let me give you an overview of techniques. You probably have seen caching in previous courses, right? Yes, you're bored of caching? Somewhat, okay. If you're bored of caching, don't be bored. There's more to be done there. Last week, I was at the HPCA conference, High Performance Computer Architecture, one of the major conferences in architecture. And IBM had a nice paper in the industrial session on their Z-series architecture. IBM Z-series is really on, these are processors, very expensive processors. Like you buy racks of these, $5 million or more. And they're supplied to banks, for example, transaction processing machines, essentially. And the goal is really to get high performance as much as possible. And these are heavy out-of-order processors with a lot of branch prediction techniques, a lot of prefetching, and many levels of cache hierarchies like L2 and L2, L3, L4, and they have virtual caching, etc. There are a lot of interesting issues. I recommend that paper for you to look at. So they have gigabytes of caches, essentially, on chip, because they actually coordinate many chips to actually form a large cache, large L4 cache. Okay, I'm bored of caching. So I'm not going to talk about caching, but I'm going to give you a quick overview of these techniques. So basically, there are fundamentally three ways of reducing techniques in reducing latency or handling latency. One is reducing the latency as much as possible fundamentally. This is a more data-centric approach. I'm not going to talk about that in this lecture, but if you're interested, look at the lectures we have in computer architecture classes. How do you reduce latency? And I think this should be done more and more. The other technique is hide the latency seen by the processor. This is a more processor-centric approach because The latency is there, but you're trying to hide it as much as possible, right? So you do caching, for example. And as long as you can fetch the data from a cache that is close by a processor, you don't see the latency because you're not accessing that part. You do prefetching, which we're going to talk about. Or there's another approach, which is tolerating or amortizing the latency seen by the processor. Again, this is very processor-centric. Multi-threading is one example. You still have the latency, but by doing something else, like executing some other thread, you hide that latency from the system, let's say. Out-of-order execution is another way of hiding the latency, right? That's really hiding latency. The latency is still there. It could be a memory latency, it could be a floating point operation latency, but you hide that latency by executing something else while you're waiting for the data dependencies to resolve. Well, we're going to talk about run rate execution, which is also a toleration mechanism. Okay, so this is actually from my PhD thesis defense and proposal. I worked on this topic, multiple of these topics actually. But there are multiple techniques. Caching we're going to talk a little bit about, and then I'm going to refer you to lectures, and then we're going to jump into prefetching. Caching is a reactive technique, meaning you bring the data into a cache, and then based on a demand request, and then you try to exploit that data for other instructions that may use that data. Right? This is a reactive or passive technique. You don't proactively bring the data. So we're going to talk about proactively bringing the data. The people have optimized the caches a lot over many years, as you can see. And all of these ideas are developed actually into the 1960s. Wilks is not the first paper, but Wilks is the first paper that's very, very clear. Okay, so prefetching, we're going to talk about this. Multi-threading works well if there are multiple threads, but it doesn't help single-thread performance. And improving single-thread performance using multi-threading hardware is an ongoing research effort, which is not easy. And out-of-order execution you've seen already. Hopefully you've loved. And hopefully you're excited about implementing out-of-order processors. Maybe. So out-of-order execution actually requires extensive hardware resource for tolerating long latencies, as we're going to see. So let me talk about caching a little bit. And there are many lectures on these topics if you're interested. So this is a modern memory hierarchy today. Again, orders may change actually, but the exact numbers can change, but you have levels and levels of caching today over here, right? The closest caches to the processor are very tightly integrated. In fact, L1 cache is really part of a processor today because you need the data supplied to the pipeline extremely quickly. And the design choices that you make in L1 cache are usually dictated by how you design your pipeline. After that, it becomes decoupled out of the pipeline and becomes part of your more on-core hierarchy. So L1 caches are small but fast. L2 caches are larger and slower. And as you get higher, as you get to higher levels in the hierarchy, you get larger capacity, but larger latencies as well. This is another picture, of course. And you could keep showing these pictures. IBM has nice pictures in their HPCA paper if you're interested. Okay. And we actually keep adding more and more levels to the hierarchy. You could, for example, have a DRAM that's a cache to some other type of memory or different types of DRAM, or you could have different types of DRAM that are not necessarily caches to each other, but one of them is small and one of them is large. We may see this later on. So essentially, we keep extending the memory hierarchy. And the reason I'm telling you all of this is because caching and prefetching principles apply to the management of all of these. There you go. Okay, so these are some slides from my DDCA lectures. Let's talk about caches quickly so that you've seen set associative caches, for example, right? 4-way, 8-way associative caches. I like thinking of set associative caches as systems where each block has a priority level in a set. It indicates how important it is to keep the block in the cache, right? And the key issue in general in caching is how do you determine and adjust the block priorities, right? So there are usually 3 key decisions you make in a set: when you insert the block, when you promote the block, and when you evict the block or replace the block. Insertion is what happens to the priorities on a cache fill. You're bringing a new block into the cache. What do you do? What do you do to the priority of that block and every other block, right? How do you sort it out? Clearly, you've seen LRU, for example, least recently used mechanism. That's one way of managing priorities. But you could also decide not to insert the block into the cache because you have a predictor that says, oh, I'm not going to reuse this block, so let me drop it. Well, let me drop it from this level of the cache. Maybe I insert it in some other level of the cache, right? So where do you insert the block? What priority level? There are a lot of papers that talk about these things clearly. Promotion is what happens to priorities on a cache hit. Basically, whenever you have a block that you access and it's in the cache, what do? Do you promote that block to be the most recently used, meaning the highest priority to keep it in the cache, or do you take some other action, right? There are different policies over here, again, which I will not go into here. You could do random. clearly, right? You could randomly change the priorities also, which may not work too badly, actually, if you're thrashing your cache. People have shown that. LRU is not the best mechanism if your cache is really thrashing. OK, eviction and replacement is what happens to priorities on a cache miss. Which block do you evict, and how do you adjust the priorities after eviction? So in DDCA, we cover some of these. I'm not going to cover these, and you probably covered some version of this, at least, in your previous class, where you learned about caches. But in multi-level caches, you have other design decisions as well. Which level do you place the block into from memory? You bring the block from memory, which level? L1, L2, L3, L4. Where do you place? Maybe all of them. Maybe none of them. Maybe a combination of them, right? Which level do you evict the block to from an inner level? So if you're evicting something from L1 cache, because you don't have enough space in the L1 cache, do you drop it? Do you write it back somewhere else? Okay. So basically, you can bypass the levels, not bypass the levels. There are many design decisions in a multi-level cache hierarchy also, in addition to the design decisions that you have inside a single level, right? OK. So there, you may have also seen inclusive, exclusive, non-inclusive hierarchies before. Yes or no? OK, very briefly, again, there's no magic over here, but inclusive means that a block in an inner level cache is always included also in an outer level, meaning that any block that's in L1 is also in L2. Any block that's in L2 is also in L3. Any block that's in L3 is also in L4. And hopefully in memory also, all of them. Yeah, basically this simplifies cache coherence. If we talk about cache coherence, you will see that. Exclusive means a block, but of course, inclusive is not good for replication. You replicate the data many times across many levels, right? So you're not utilizing your chip space nicely. Exclusive means a block in an inner level does not exist in an outer level. So L1 is exclusive of L2, which is exclusive of L3, which is exclusive of L4. Hopefully, memory includes all of them, though. Memory, because memory is where you get the blocks from, right? I mean, you could imagine a system where memory doesn't include that, and you go to storage, right? So memory could be exclusive of storage, but that's a design choice that people have not taken yet. But basically, the exclusive is good because it better utilizes space in the entire hierarchy. There's little redundancy, but it makes cache coherence harder because you need to check all of the caches for keeping them coherent. Most processors today use a non-inclusive approach or an exclusive approach. A block in an inner level may or may not be included in outer levels. This relaxes a lot of design decisions, like prefetching, for example. When you prefetch something, you evict a block. Do you write it back somewhere else? You actually don't need to make a very strong decision to keep inclusivity or exclusivity. OK. So there are a lot of works that try to improve cache performance, which we're not going to cover. But this is just to show you that this is also a rich area. Yes?
With the non-exclusive or with the exclusive policy, it's clear, but like with the non-inclusive policy, if the L1 entry is the newest entry, and maybe L2 has an older entry that hasn't been cleared yet, what happens if the L1 entry gets cleared? Sometimes they get cleared pretty randomly.
Yeah.
Like, this would lead to a wrong value. You know?
Well, all of these policies, you need to make sure correctness, right? If your L1 has a dirty data, you should propagate it to memory in some way. Maybe you don't write it to L2. You need to invalidate the L2. So there's a coherence problem that you need to handle. Yes. So I'm assuming that there's a way to maintain correctness. Yeah, you need to update, basically. OK. So there are a lot of ideas, again, some of which we cover in other courses, including DDCA. If you're interested, you can look at DDCA. But there are also other courses that we have on cache optimizations. I'm not going to do that, unless you really want to do that. But I'm going to jump to prefetching. Make sense? Caching is an area that there's been a lot of work on. Like it's at some point, International Symposium on Computer Architecture was called International Symposium on Cache Architecture. There were so many papers on caches. OK. Prefetching. OK, prefetching is a more proactive approach, meaning you try to fetch the data before it's needed by the program, as opposed to relying on demand requests to bring the data in. That's why it's called a prefetch or preload. Because memory latency is high, and if we can prefetch accurately and early enough, we can reduce or eliminate that latency, right? That's the hope. It can eliminate compulsory cache misses. You may have heard of compulsory cache misses. Compulsory means basically it's a cache miss that you have to have, assuming what you're doing is only caching. Right? With the demand miss, your cache doesn't have it yet, so you have to wait for that to fill the cache. Right? It can also eliminate all misses, actually. Like capacity means you don't have enough capacity in your cache. Conflict miss means you don't have enough ways in your set, in a single part of your set. Coherence means you get a cache miss because some other processor invalidated your cache block. Prefetching can actually handle all of these if you design the prefetcher nicely, let's say. It can target coherence misses. It can basically it can fix all of these. But of course, you need to predict which address will be needed in the future, which of course means that this works if programs have predictable misaddress patterns. Then the question is, what does that mean? What's a predictable pattern, right? Okay. Now you can think about machine learning also to predict, and we're going to do that also a little bit. Okay, so one thing to keep in mind is, as opposed to branch prediction, which we have studied, a misprediction in prefetching doesn't affect correctness. You basically get a wrong address, wrong data, but you simply don't use it. Right? Does that make sense? Of course, you should not prefetch. Basically, you should really not change the state with prefetching, change the architectural state with prefetching. Right? This is assuming that you don't change the architectural state. As a result, there is no state recovery. But if you mispredict a branch, for example, you go on the wrong path, and you have to recover to go on the correct path again. Right? Here, you just simply don't use the data that you fetch. Okay. So in modern systems, prefetching is usually done at the cache block granularity because we have caches, and you try to prefetch blocks, essentially. But it doesn't have to be that way also. If you have sectored caches, for example, where you have smaller sub-blocks, you can prefetch sub-blocks, etc. It's a technique that can reduce both miss rate and miss latency of caches. And it can be done by anyone, essentially. It can be done on hardware. We're going to look a lot into hardware. But it can be done by the compiler, programmer, or the system. It can be done at a higher level also, right? For example, we have operating systems, and operating systems actually manage a lot of programs. Before I launch a program, it may have already prefetched the program's data that it expected me to launch at this point in time, right? Windows, for example, at some point had a sophisticated machine learning-based prefetcher that tries to predict what program a person is going to use and preloads the data, pages of that program from hard disk into the main memory. Right? And you can do that clearly at the system level. We're going to talk a lot about hardware in this course. This is a very old paper that we wrote, 2005, just to show you that prefetcher can be anywhere in the memory hierarchy. And today we have prefetchers everywhere in the memory hierarchy. This is an example over here. We were looking at stream prefetchers. I'm going to mention that later on. It basically monitors accesses coming into an L2 cache. It also looks at what is missing in the L2 cache, and it decides what to start prefetching at the lower from the main memory into the L2 cache, for example. But you could imagine prefetchers everywhere in the system. Okay, there are 4 major questions in prefetching. I'm going to go through these, and then we're going to talk about some prefetching algorithms. What, when, where, and how. What addresses do you prefetch? What is your algorithm to decide which address do you prefetch? When do you initiate a prefetch request? Are you early, late, or on time? Hopefully early, or on time. On time is the best, actually, not even early. Where means multiple aspects of where. Where do you place the prefetch data? Do you put it in a cache or prefetch a separate buffer? Most processors today use caches because separate buffers complicate the memory hierarchy, which is already quite complicated. Where do you place the prefetcher? Which level in the memory hierarchy? Today, essentially, we have prefetchers essentially everywhere. You can have prefetchers from into the L1 cache, into the L2 cache, into the L3 cache, and also in the memory controller on the memory side a little bit. And then how does the prefetcher operate, and who operates it? Is it the software? Is it the hardware? Is it a hybrid mechanism? Is it execution-based? We're going to see some examples of these. Does that sound good? Now let's tackle these questions a little bit more. So what address do you prefetch? Because this is critical in the end. If you don't prefetch the correct address, you're wasting resources. Many resources that are critical, like memory bandwidth, cache or prefetch buffer space, energy consumption. And these could all be utilized by demand requests or more accurate prefetch requests, right? That's the idea over here. You don't want to waste these resources. So accuracy is very important in prefetching. This is accurate prediction of addresses to prefetch. Prefetch accuracy is defined as what is the fraction of prefetches that are used by the program divided by the total number of prefetches that you sent. Right? Ideally, you want this to be 100%. But unfortunately, you don't get to 100% unless you're very conservative. And when you're very conservative, you may not be able to prefetch much. Right? Okay, so how do we know what to prefetch? One way of doing this is to predict based on past access patterns. Right? And we're going to see a lot of that. Or you can use the compiler's programmer's knowledge of data structures, such that you can create a thread, for example, that does prefetching for the main program. You can have a separate thread prefetching for the main program. They're running on the same core or different cores, and one of them is prefetching into the cache before the main thread touches those blocks, right? That's certainly possible. You could have purely software methods of doing that, or hardware, software, cooperative methods of doing that. So prefetching algorithms determines what to prefetch. We're going to see some examples of this, including some things that are implemented in existing processors. Okay, so let's go through this exercise. How predictable are these access patterns? The first one, hopefully you can predict what's coming next, right? A plus 5, 6. Hopefully you can predict this one also, plus 42. So this is called a stride. Here you have a stride of 1. These are, again, assume that these are cache block addresses, and the processor is touching a cache block address A plus 1, A plus 2. So the stride is 1. Here the stride is 42. And you can easily design logic to determine the stride. It's called a stride detector, essentially. A little bit harder, but also predictable, hopefully. So what do you have here? Plus 2, plus 3, plus 4, plus 2, plus 3, plus 4. And it keeps going. So now you can actually have a way of predicting the deltas, the pattern, plus 2, plus 3, plus 4, right? Okay, this is a bit harder, maybe. At least you can get some patterns, like I see XYT, 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 XYT. At least when I see X, I can bring Y and T, even though these addresses may have no stride associated with them, right? Now think about the hardware implications. It's a bit harder to design hardware for, right? Okay, and then another one over here, which I'll let you figure out, but this is also doable, I believe. The interesting thing over here is A, Z, and P may have nothing to do with each other, but you're really touching the same set of deltas from that base, right? You have a base A, Z, and P. Assuming you figured out that you're touching these deltas, whenever you see Z, something totally different from A, you give these deltas and prefetch all of them at the same time, potentially. Right? Again, this requires recording of these deltas. Okay, so all of these are predictable, as you can see, except this is the hardest one, I would say. Okay, so that's think about now algorithms to prefetch them. Let's move to when. When do you initiate a prefetch request? Again, I'm not going to give you answers over here, but there are trade-offs associated. Prefetching too early leads to prefetch data not being used before it's evicted from caches, for example. Prefetching too late might not hide the whole memory latency. So you need to find a sweet spot to initiate the prefetch rate. This is called timeliness, essentially. When a data item is prefetched, it affects the timeliness of the prefetching. And ideally, we want perfectly timely prefetchers that bring the data into the cache right before the processor needs it. Right? Prefetcher can be made more timely by making it more aggressive, meaning you try to stay far ahead from the processor's demand access stream in hardware, or you move the prefetch instructions earlier in the code. If you're doing software-based prefetching, you normally have prefetch instructions, and that goes earlier. Or if you're doing a thread-based prefetching, like I gave you an idea of, you could launch the thread much earlier. Of course, the downside is, if you do it earlier, then you may not get to the thing that is going to access that data, right? Because there are branches in the code, right? Okay, let's take a look at this aggressiveness in this picture. For example, here, you may say, oh, I'm going to be very aggressive. I'm going to predict that this stream is going to last, I don't know, up to A plus a million. And you keep generating prefetches early on, right? 1 million prefetches. And then the processor stops at A plus 4. Sounds pretty aggressive, right? So that's, hopefully that gives you the idea. You could do it with all of these access patterns, actually. You could multiply the stride by number of times you generate the request by adding that stride to the previous thing that you generated. Okay, so that's one essentially. And people struggle with this when they design prefetchers. Okay, where there are multiple aspects of where do you place the prefetch data? You could place it in cache or in prefetch buffer. Cache is simple, no need for separate buffers. But of course, the downside is it can evict useful demand data. It could cause cache pollution. So people develop techniques to decide where to insert the prefetches. So everything that I said, promotion, insertion, eviction, is affected by whether you're putting a prefetch into the cache, right? That affects your demands, that affects your prefetches also. Right? Alternatively, you could make it clean and put things in a separate prefetch buffer, which protects the demand data from the prefetches. No cache pollution in this case. So basically, evicting useful demand data is called cache pollution. Unfortunately, there's a lot of downsides over here, which are kind of partially listed. Your memory system design becomes more complex. Where do you place the prefetch buffer? If you have multiple prefetchers, do you have multiple prefetch buffers? When do you access the prefetch buffer? Do you access parallel or serially with the cache? When do you move the data from the prefetch buffer to the cache? And there needs to be alternate paths to do that. How do you size the prefetch buffer? If your prefetcher is aggressive, this buffer becomes as big as the cache actually. So there are a lot of issues over here. And keeping the prefetch buffer coherent is probably the easiest one among these issues, frankly. So this is not done in general. Many modern systems place the prefetch data into the cache in the end because of all of these headaches. Okay, there's also which level of cache to prefetch into, and the answer today is you can prefetch into almost every level, potentially using different prefetchers, right? So you can see from memory to L4, L3, L2, or memory to L1. L1 is a bit special because it's very precious in terms of capacity. Normally, people use separate prefetchers into L1, but there could be separate prefetchers into L2 also, because L2s are also quite small today, relatively, right? Things are becoming larger relatively, but L2s are quite small. L1 is the most precious thing because in the end, L1 is really dictated by the pipeline design decisions that you make. Okay, and then there's where to place the prefetch data in the cache. We kind of talked about that briefly. Do we treat the prefetch blocks the same as demand fetch blocks? Bad idea in general, because prefetch accuracy may vary. So you may want to actually decide the priority of a block based on the prefetch accuracy, for example, or timeliness, or you could use multiple metrics. And prefetch blocks are not known to be needed. For example, with LRU, a demand block is placed into the MRU, most recently used position. Is that a good idea? Even processors that use very simple policies like LRU policies don't place the prefetches into the MRU position when they bring the data. They put it somewhere else in between. Okay, so you can actually skew the replacement policy such that it favors the demand fetch blocks in some way. Okay. Then there's another aspect of where do you place the hardware prefetcher in the memory hierarchy, right? Again, it could be everywhere. In other words, what access patterns does the prefetcher see? L1 hits and misses, L1 misses, L2 misses. Again, you can generalize this to anything. The key distinction, I think, is you see what kind of access pattern does the prefetcher see. If you, for example, see every access that is made by the processor, you see a complete picture. But that's a lot of bandwidth also that you need to deal with because the processor is generating addresses every cycle, multiple addresses every cycle, actually. And if you have an aggressive processor. But seeing a more complete access pattern can give you potentially better accuracy and coverage. But prefetcher needs to examine more requests, so it becomes more complicated to keep up with the processor. Seeing a less complete access pattern may not be that bad. You can find predictability. Because what happens is as L1 cache sees all the accesses from the processor, right? L2 cache sees a filtered set of accesses, filtered by the locality that you can exploit in L1. L3 cache sees an even filtered set of accesses, and the memory controller sees an even filtered set of accesses. So you can think of caching also the same way, right? It makes no sense to have the same policy that you use in L1 to be replicated in L4, because these are very different types of locality that you see actually. One is very filtered locality. The other is everything that the processor touches. So think about it. That's why existing systems use very different policies at different levels to manage the caches. All of those promotion, insertion, eviction policies that I mentioned are different at different levels. So prefetching could be different also. And it is different, actually. OK, so this is our modern memory hierarchy, just to complement what I just said over here. And then there's more memory. And then there's more memory, actually. Today, data centers, for example, they don't stop at local nodes. If you don't have enough memory in a local node, well, why not have a remote node supplying you with more memory? Right? This is what happens in large-scale data applications. This is just to give you a bigger picture. You may actually have a disaggregated memory also remotely, but this doesn't have to be disaggregated. It could be some sort of memory blade, or it could be some other node that supplies a little bit more memory. Which is what's done in the IBM paper that I actually mentioned in HPCA. So a memory hierarchy extends beyond a single server, enables higher capacity, but now you have a prefetching problem, another prefetching problem, right? If this processor touches something remote, how do you get it over here as soon as you can, right? Okay, there are a lot of interesting papers in this direction if you're interested. Okay, now let's talk about how. How is also very interesting. You can also have a combination of all of these, but there's software prefetching, which I will spend less time on because it's very hard to get it right in today's systems unless you have very, very regular programs. Hardware prefetching, which is what's done in most systems today, well, essentially all high-performance systems today. And then there's execution-based prefetching, which is actually very interesting because it covers a lot of different things. Okay, software, ISA, instruction set architecture, provides prefetch instructions, and the programmer or compiler inserts prefetch instructions into the program. This clearly requires some effort, right? And usually this works well for regular access patterns. Hardware, you have specialized hardware, monitors memory accesses coming from the processor. And it's basically whatever you pick, memorizes, finds, learns, address strides, patterns, or correlations, and generates prefetch address automatically. Software is not involved in pure hardware mechanisms, right? Basically, hardware needs to answer all of those questions. When do I generate a prefetch request? How aggressive I am? What kind of things can I detect, etc. Execution-based, you could think of it as pure software. It could be pure software. It could be pure hardware. It could be hardware-software cooperative. That's why I call it execution-based. But essentially, what distinguishes these from these other ones is you execute a thread, software thread, or hardware thread that could be invisible to software, invisible to the operating system potentially, to prefetch data for the main program, right? It can be generated again by the software, programmer, or hardware. And we're going to talk about that. My PhD thesis was actually on execution-based prefetching. We'll discuss that. So this is a prefetch instruction, x86. It's complicated. This is from one version of x86. Essentially, you can see over here, move data from M8 closer to the processor using some hint. Kind of doesn't make sense if you read this, right? T0 hint, T1 hint, T2 hint, and NTA hint. And if you look at the description, it also kind of doesn't make sense. I mean, mostly, right? For example, temporal data. Prefetch data into all levels of the cache hierarchy. In Pentium 3 processor, first or second level cache. In Pentium 4 Intel Xeon processor, second level cache. Clearly, the first level cache is not part of the all levels of the cache hierarchy. So this shows you that people are actually a little bit confused in the specification for good reason, because it's hard to, let's say, relinquish control to the software completely as a hardware person doing this ISA description, right? So basically, your goal is to enable prefetching from the software, but again, at least in this particular description of the ISA, you don't get a lot of control. You cannot basically prefetch into the second level cache in later processors. In earlier processors, maybe you could. Okay. And essentially, they look kind of the same, right? Okay. But basically, you can use these instructions, and these instructions are non-blocking in general. They generate a prefetch request, and they don't stall the instruction window because they don't prefetch data into a register. There's no register dependencies. And in many cases, if the architect is having difficulty getting the system right, they drop these instructions. So you may actually insert a prefetch instruction in your program, and the architect says, oh, this is not something I have to execute. Let me drop it. It happens. These things happen. And there's good reason for it. Well, one of the issues is basically software prefetching. Even though it's been developed, it has not been as successful because it's very hard to, like, I would recommend you to watch the DDCA lectures because we don't have time, but because it's very hard to get it right. Where do you insert this prefetch request, right? A lot of things is dependent. So you have a program. You need to fetch some data, and you need to decide where to insert the prefetch request. The distance between those two instructions is dependent on the memory latency, effectiveness of your caching, all of the latencies that you experience in your interconnect. So it's very hard to decide a good distance in the end, unless your program is extremely regular and you actually control the caches using tiling, blocking, etc. So it is possible to do that. But then maybe you do better forms of prefetching, right? You don't need these prefetch instructions potentially. Okay, so this is a hardware prefetcher, which we will talk about. This is streaming prefetcher. Again, this is a high-level concept over here. And the idea is the processor is touching line 0, line 1. They're in L1. And the processor detected a stream, so it keeps prefetching line 2, line 3, line 4, line 5, and then the remaining lines from the memory. So it's really streaming data initiated by the core for the next lines. This is streaming because the stride is equal to 1. Stride could be something else, and you could still be streaming with a larger stride, right? So this is actually implemented in IBM Power 4. They have a nice paper about it when people used to write papers about processors. There's actually a very nice long paper about the Power 4 microarchitecture. If you're interested, you can look at it. Unfortunately, IBM stopped doing this Journal of Research and Development, which was actually a really nice resource for everyone. No. So you cannot read about their latest processors except for the industry session of HPCA. Okay. So this is where the stream prefetching idea was developed. This is a beautiful paper by Norm Juppy. And again, it's the same idea that is implemented in this processor and many other processors. One of the reasons I am showing you this paper is basically to show you what things were like. So these are times in 1970s. VAX was the king of processors at the time. It built a lot of auto order processors. You can see that the cycle time is 200 nanoseconds over here. Cycles per instruction is 10 at the time. Memory time is 1200 nanoseconds, and missed cost is 6 cycles. And missed cost in terms of instructions is 0.6 instructions. So instructions executed in the processor were actually cheaper than a memory access in terms of latency, if you think about it. Right? Over time, it became much worse. So this is what the processor, this thing is designed for, stream prefetching, WLI Western Research Lab Titan processor. Missed cost is about 12 cycles. And in terms of instructions, that's 8.6 instructions. And the projection is 140 instructions. So this IBM paper at HPCA, their memory access latency is about 700 cycles, processor cycles, at a 5.5 gigahertz processor. That's a very long memory access latency. And he said that they could cut it by probably 200 cycles if they optimize things, but not lower than that. So think about that. Today, we're at actually at least 500 cycles. When I was at Microsoft, at Xbox 360, memory latency is 650 cycles. For a slower processor, of course, not 5.5 gigahertz, but still, these are very long latencies today. So we're actually at a point where latencies are a bit crazy. So this is an example of execution-based prefetching. These are actually real ideas that have had real impact, as you can see. Sun implemented a version of what we have proposed in my thesis, or papers actually, before my thesis. And they basically show that you can get better performance by keeping the same cache size, or you can keep, you can have a prefetcher implemented with 1 megabyte cache, and that gets you the same performance as an 8 megabyte cache without a prefetcher. So a prefetcher is a good way of potentially reducing your hardware complexity, right? As opposed to implementing higher and higher cost caches, maybe you design better and better prefetchers, right? That way you don't need to store that much data. Again, we're going to talk about the Scout, but this is essentially run-ahead execution. But I think the reason I show you this is multiple reasons. One is execution-based prefetchers exist, hardware-based prefetchers exist, software-based prefetchers exist. Effective prefetch, and also the second reason is effective prefetching can improve both performance and reduce hardware cost. Makes sense, hopefully, right? So the hardware you're spending on things can actually be buying your hardware somewhere else, right? Okay, let's talk about metrics a little bit. I mean, the ultimate metric is really performance and energy in the end, right? But there are auxiliary metrics that you use to try to optimize a prefetcher potentially, right? Because ultimate metric may not be easily optimizable without knowing what's going on underneath, right? So accuracy we've already discussed, right? The used prefetches divided by sent prefetches. Coverage is also important. What is the fraction of misses that you correctly predict out of all the misses that are generated by the program, right? Ideally, you would like that to be 100% also. You would like 100% accuracy, 100% coverage, perfect timeliness. You cannot get all of them, unfortunately. You can get maybe 2 out of 3. Okay, timeliness is, it could be defined in multiple ways, but a very strict definition is the fraction of on-time prefetches divided by total number of prefetches that are actually needed by the processor. That's a strict definition. What is on time, right? It's actually in the cache when the processor accesses it. That's one definition. This doesn't cover the cases where the data was just being put in the cache one cycle after the processor needed it, right? So there's actually coverage in terms of time also, but there are multiple metrics. There are also other metrics like bandwidth. This is how much usually prefetching increases bandwidth because you're not perfectly accurate, right? And this is the memory bandwidth consumed with the prefetcher divided by memory bandwidth consumed without the prefetcher. Now, this is not always bad. Increasing the memory bandwidth is not always bad because if your bus bandwidth is idle, sometimes you can utilize the idle bandwidth to do prefetch. In many systems today, it may or may not be the case. So don't count on bus bandwidth being idle, especially in data-intensive programs. So we talk about cache pollution also. These are extra demand misses due to prefetch placement in cache. It's more difficult to exactly quantify, but it affects performance because it depends on the time window you're looking at, right? But it's possible to quantify it approximately. So these are all auxiliary metrics to keep in mind. And if you have a very aggressive prefetcher, usually your coverage increases, your timeliness becomes better, your accuracy tanks, your bandwidth consumption increases, your cache pollution increases. If you have a very conservative prefetcher, your accuracy may be almost 100%, your coverage is low, your timeliness not so good probably. Your bandwidth consumption is good, cache pollution is good, but you're not getting much performance, right? So basically, deciding on the aggressiveness of the prefetcher is important. Okay, this is one paper that we had written. We're going to talk maybe more about that, but this talks about a lot of these metrics and how to use accuracy, coverage, mainly accuracy, timeliness, and pollution to decide how aggressive you should really make your prefetcher, and also where should you insert your prefetches in the cache. So I can dynamically adapt all of those. Any questions? Okay, so let's now talk about, we kind of talked a lot about theory. Let's talk about some mechanisms. So I'm going to start with stride prefetcher. We're going to detect the strides, and you can already imagine a circuit that detects it, basically. The idea of this prefetcher is to record the stride between consecutive memory accesses. And if the stride is stable, so you have some confidence mechanism again, use it to predict the next M memory accesses. M depends on your aggressiveness, right? Okay, sounds simple, right? You build confidence. For example, you record A plus N, and you say, oh, okay, the stride is probably N, but I'm going to wait. And then you see the stride N again. You increment a counter saying that I saw the stride twice. Well, I'm going to wait. You saw the stride 3 times. Okay, something is happening. I'm going to prefetch next M incarnations of the stride. Okay, so that's one way of doing it. Now, even this actually has multiple versions, let's say. You can determine the stride on a per instruction basis. So you can do this for every PC program counter, or you can do it on a per memory region basis, right? And these have different implications. So this is instruction-based stride prefetching. Essentially, you have a table that's indexed with the program counter, and you have a tag for the program counter. You look at the last address reference, cache block address, again, for that program counter and the last stride that you've seen. And you have some confidence level that I just mentioned. So if you keep seeing the same stride for the same PC, your confidence level increases and you keep generating prefetches, right? That's the idea. I mean, it may be a little bit more complicated than this, but this is the basic idea. So this way, each load or store instruction can lead to a memory access pattern with a different stride, right? So you can distinguish strides that are potentially unique to different load instructions. Now, you can only detect those strides caused by each instruction. You cannot see strides across different sets of instructions, right? So timeliness of prefetches can be an issue, but you could solve it. Essentially, initiating a prefetch when the load is fetched the next time can be too late because you may be fetching this load very soon, right? So you need to look ahead in the instruction stream. And people have done multiple ways of looking ahead. One way of looking ahead is basically you don't prefetch just the next one. You prefetch the next N ones, right? Next N incarnations of that stride for that. Okay, so that was instruction based. You could do this on a memory region base, which is a little bit more complicated, but you divide memory into regions. And based on the cache block address, you index, this is a region table. For a given region, you have a tag, and you have a stride in that region. Meaning, whenever I access this region, I have the stride, and I'm going to add this stride to this address. There could be another address that you keep over here, of course, to decide what is the last address that you have fetched in that region, and you're going to add a stride over there. Now, the advantage of this is this can detect strided memory access patterns that appear due to multiple instructions. Let me finish the slide, and then we're going to stop. For example, here, the stride may be happening where each access could be due to a different instruction, different load, right? It's possible. There are access patterns and programs that make this happen. Now you can detect it. Now, stream prefetching. Stream buffer is a special case of memory region-based stride prefetching where N is 1. And that was IBM Power 4. Okay, I think I've said all of this, almost. But basically, the latter is more hardware intensive. The memory region-based is a little bit more hardware intensive, but it's actually used in many processors. Many processors actually use instruction-based stride prefetching also. For example, Intel, an example, where when they used to write papers, they talk about that. and also a memory region-based stream prefetching that we've seen. Okay, this is where we will pick up. We're going to get more complicated. We're going to talk about like more advanced prefetching mechanisms, and then hopefully we'll conclude prefetching next time. Any questions? Burning? Nothing is burning. Okay, good. You can ask next time.